Imperfections in solids. Crystalline solid state is characterized by a three-dimensional periodic arrangement of atoms or ions or molecules in space. Ideally, there should be a perfect order in this arrangement. However, crystals in nature are not perfect. They do not possess perfectly ordered arrangement. This is due to the presence of few impurities or due to dislocation of few of constituent particles from their normal positions. Any deviation from the perfectly ordered arrangement of atoms or ions or molecules in crystal is called imperfection or defect. Defects can be classified into two types: point defects, line defects. Point defects. Point defect can be defined as the irregularities or deviations from ideal arrangement around a point or an atom in a crystal. Line defects. Line defects are defined as irregularities or deviations from ideal arrangement in entire row of lattice points. In this chapter, we will learn only about point defects. The point defects can be further classified into stoichiometric defects, non-stoichiometric defects, impurity defects. Stoichiometric defects. If imperfections in a crystal are such that the ratio between the cations and anions remains the same as represented by molecular formula, the defect is called stoichiometric defect. These defects are also called thermodynamic defect or intrinsic defect. The stoichiometric defects are of two types: vacancy defect, interstitial defect. Vacancy defect. In a crystalline solid, some of the lattice sites are vacant. The crystal is said to have vacancy defect. This generally arises due to the absorption of heat from the surroundings, which results in the decrease in the density of the substance. Interstitial defect. Interstitial defect is caused when some of the constituent particles, can be atoms, molecules or ions, are present in the vacant spaces in the crystal structure. These vacant spaces are known as interstitial sites, and the particles present in these vacancies are known as interstitials. As the number of particles within the crystal increases, the density of a substance increases. Both vacancy defect and interstitial defects are generally shown by non-ionic solids. Ionic solids do not show these simple vacancy defect and interstitial defects. Instead, they show Schottky and Frenkel defects. Schottky defects. Schottky defect is similar to vacancy defects. This type of defect is created when equal number of positive ion and negative ions are missing from their lattice sites, so that electrical neutrality is maintained. Here, mass decreases while volume remains the same. Presence of a large number of Schottky defect site lowers the density of the solid. Types of compounds exhibiting Schottky defects. Schottky defect is shown by highly ionic compounds which have high coordination number and small difference in the cations and anions. A few examples of ionic compounds exhibiting Schottky defect are NaCl, KCl, KBr, AgBr, and CsCl. Schottky defects maintain the electrical neutrality of the crystal. In sodium chloride, there are about 10 raised to 22 ions in 1 cubic centimeter of sodium chloride, and there are approximately 10 raised to 6 Schottky pairs per cubic centimeter at room temperature. Therefore, in sodium chloride at room temperature, there is 1 Schottky defect per 10 raised to 16 ions. Frenkel defect. If in an ionic solid, a smaller ion, generally cations, goes missing from their lattice site and occupies the interstitial site such that electrical neutrality as well as the stoichiometry of the compound are maintained, this type of dislocation is called Frenkel defect and also called as dislocation defect. This defect is a combination of vacancy defect and interstitial defect. It is a vacancy defect at its original site and an interstitial defect at its new location. Since no ions are missing from the crystal as a whole, Frenkel defects do not affect the density. Frenkel defects are common in ionic compounds which have low coordination number and large difference in size between cations and anions. Frenkel defects are found in silver halides due to the small size of silver ion and in zinc sulfide due to small size of zinc ion. In pure alkali halides, Frenkel defects are not observed because the ions are bigger than the voids. Impurity defects. So far, we have discussed point defects where there are no foreign atoms. Foreign atoms can occupy interstitial sites or lattice sites in a crystal. Defects in the ionic solids may be introduced by adding impurity ions. If the impurity ions are in a different valence state from that of the host ions, vacancies are created. Let us understand with the help of an example. Consider the crystallization of molten sodium chloride in presence of small amount of strontium chloride, SrCl2. During crystallization process, some of the sodium ions are replaced by strontium ions, Sr plus 2. For every Sr2 plus ion, 2 Na plus ions are removed to maintain electrical neutrality and also creates a cationic vacancy. Similar type of defect and behavior is observed when CdCl2 is added to AgCl.